Good evening and welcome to the fifth lecture this year sponsored by the Space Science and Engineering Center. Our speaker tonight is Dr. Christopher McKay, who has been working in the search for life on Mars through a variety of different ways for many years. I picked a very bad night for this lecture tonight, considering that this is the Green Bay Packers-Dallas game. And so instead of wasting any more time introducing him, let me just welcome Chris McKay to give us a lecture on life on Mars, past, present, and future. Chris?
Thanks, Sanjay. What I'm going to talk about tonight is what we know about Mars, a little bit of what we've learned from previous missions, and about a little bit about the meteorite evidence, how we know the meteorites came from Mars in particular. And then I'm going to talk mostly about what should we do next. If we want to get more information about Mars and about the possibility that it had life, where should we go? The answer is not the Pacific Ocean. Where should we send the next spacecraft? Then I'll talk at the end a little bit about the future, the long-term future that for Mars as well. Let me see if I can get this to work. This should be a remote control. Great. This is a picture of Viking from orbit, looking down on the surface of Mars. And I want to just remind you a little bit of what we know about Mars from Viking. Viking landed in 1976, over 20 years ago. And the reason Viking went to Mars was to search for life. Its objective, it had an arm. Viking had a robot arm that reached out and scooped up into the soil and scooped up a handful of dirt. You can see the trench that the arm dug. And Viking's main job was to see if there was any microorganisms in that dirt. And it did it doing a series of simple experiments where it took some of that dirt and basically added nutrient to it, added chicken soup, and to see if there was anything that would eat the soup. And then it took some of the dirt and shined a light on it to see if there's anything that could photosynthesize. Interestingly, all the biology experiments on Viking had some kind of activity. When the soup was added, the soil fizzed and released oxygen. And when nutrients were added, something in the soil broke down the nutrients. But Viking also had an instrument that analyzed the soil, looking for organic material, the stuff of which all life on Earth is made, and it didn't find any at the parts per billion level. So it's very hard to think that the results that Viking found in its biology experiments were life if there's no organic material in it. So what Viking basically said is Mars is dead. Dead as a doornail. Right now, the surface of Mars is dead. But that's not the most interesting results of Viking. Let me just remind you a little bit about what Mars is like, and this is important to understand why it's dead, but why it's still interesting. The Mars atmosphere is shown here, mostly carbon dioxide, small amounts of nitrogen, argon. It's the same atmosphere as Venus. It's very different than Earth's atmosphere, which is oxygen and nitrogen, of course. But in some sense, Earth's atmosphere used to be like this. We think early in Earth's history it had a carbon dioxide atmosphere. And only recently, the last couple billion years, has the carbon dioxide been replaced by oxygen. And in fact, human beings, in their wisdom, are getting rid of the oxygen and bringing back the CO2 and restoring the Earth to its original environmentally correct atmospheric composition. So the atmosphere of Mars is not surprising. The composition is what you'd expect. What is surprising about Mars' atmosphere is how thin it is. This is the pressure over 3 Mars years, 6 Earth years in units of millibars from 7 to 10. Sea level on Earth is 1,000. So the Mars atmosphere is 100 times thinner than Earth's atmosphere. To have an atmosphere this thin on Earth, you'd have to move up about 20 miles high in the atmosphere. The atmosphere is so thin that water at body temperature, at skin temperature, would boil. The vapor pressure of water at body temperature is about 60 in these units. So that's why if humans go to Mars, or when humans go to Mars, they'll have to use a spacesuit because the pressure is so low. It's also important from the point of view of water because the triple point pressure of water is 6 millibars, which means that water on Mars, because the pressure is so low, behaves like dry ice on Earth. If you imagine a chunk of dry ice, solid carbon dioxide, frozen carbon dioxide, as it warms up, it goes directly into vapor. It doesn't form a puddle of carbon dioxide. Water would behave the same way on Mars. And that's fundamentally why Mars is dead. Today, the surface has no liquid water at any point at any time. It doesn't mean there isn't water. This is one of my favorite scenes from Viking. Looking out on the surface of Mars, you see these white patches here? Let me use a pointer. See these white patches? That's frost. This is a cold morning on Viking, on the surface of Mars. Frost is formed. The sun's going to come up and warm the surface, and this is going to vaporize. It's never going to form a little puddle on the surface, though, because the pressure is so low and the temperatures are so low. And this is an important fact. Today, on the surface of Mars, there is never liquid water at any place or any time. And we think that's fundamentally the reason why the surface is devoid of life, why there's nothing living there. But what Viking also showed us is that at one time, Mars had lots of water. Here's an image showing teardrop-shaped islands. Something flowed through here. These round things are craters. This is evidence that at one time there's a huge river here. This scale bar is 100 kilometers, that's 60 miles. So these are big features showing what was obviously floods flowing, a lot of water at one time flowing on the surface of Mars. Here's another image, about 300 kilometers across, a couple hundred miles across, and one can see clearly flood features flowing here. Here's a crater with flood features flowing out from it, water flowing out from it. At one time, Mars had big rivers. These rivers are as large as rivers in North America. These are large rivers. Mars had water at one time. Here's another flood feature, fluvial feature. But this one's from Venus. This one is obviously not liquid water, even though it looks sort of like it. It was carved by lava, by a low viscosity carbonate lava on Venus. The temperature was 600 degrees when this one was carved. So one has to be careful just seeing something that looks like a river to jump to the conclusion that that means it was water. On Mars, though, we can rule out lavas. This is a good example of a Martian feature that makes us think that it really was water. This is a valley where channels come together to form bigger channels, forming bigger channels all the way to a very large channel. In order for this to have been carved by lava, one would have to imagine many, many volcanoes spread all over this watershed, which is really not a viable. It's not consistent with the geology of the feature of this feature. So there's other possible liquids, but liquid water is the explanation that really does the best job of explaining these features. So we think that at one time Mars had lots of liquid water. We know that that was long ago because we see these craters. These craters say that this ground is very old ground. It's 3.5 billion years old. So Mars had water 3.5 billion years ago. There's also evidence that Mars was more active geologically billions of years ago. This is Olympus Mons, the largest volcano in the solar system. It's 27 kilometers high. That's 16 miles high. It's 3 times higher than Mount Everest. This is a huge volcano, 500 kilometers across at its base. It's a giant volcano, and it's not alone. There's several of these on Mars, several large volcanoes and volcanic structures on Mars, all saying that at one time Mars was more active. It had volcanoes that was flowing, it had rivers, presumably it had lakes and maybe even oceans. All of this occurring billions of years ago. And I think a very nice pictorial representation of this is shown in the next image, which shows an artist's conception of what Mars might have looked like 3.5 billion years ago. Sometimes I tell people this was taken with the Hubble Space Telescope because it sees backwards in time, but it's not really the case. What this picture is if we look at the size of the rivers and see how deep they are and how wide they are, and calculate how much water is required to have carved all those river features, and then take that amount of water, which turns out to be equal to a layer 500 meters thick over the entire planet, and let that layer of water relax into the present topography. Just let the water flow where it would on Mars. This is a correct representation of what 500 meters of water would look like on Mars. You'd have an ocean in the north, the northern lowlands, and the Valles Marineris Canyon system would be full of water, but Tharsis would be above water as well as a large part of the southern highlands. So this is what Mars might have actually looked like. And the amazing thing about this picture, of course, is when you look at it, it must remind you of the Earth from space, the famous blue marble picture, the Apollo 17 image of the Earth from space. And that's exactly the point. We think that at one time there were 2 blue marbles in our solar system, Earth and Mars. And the question, of course, is what happened to one of our marbles? We lost one of our marbles. It's not there anymore. Why did Mars not retain the water-rich world that it had at one time? And that's the question. It's the comparison of Mars, this early Earth-like phase, to Earth that's now the focus of the search for life on Mars and the question of life on Mars. Let me now just do a little more detail about comparing Earth and Mars. This is a timeline showing the history of the Earth from 4.5 billion years ago to now, right here. And the only point is a little bit out of focus, I guess, but I don't know if I can control that from here. The Earth forms about 3.8 billion years ago. The Earth is forming. The last little bits and pieces of the Earth are coming together, and we have, right away, definite evidence for life at 3.5. And by definite evidence for life, I mean clear fossils in the fossil record which show microalgae and bacteria clearly there at 3.5. Unambiguous evidence of biology at 3.5. Now at 3.8, we have chemical evidence of life. We find the remnants, organic material, that have the pattern consistent with life. As I'll show you later, living systems have a chemical signature in the carbon from which they're composed. Well, this is the period on Earth, 4 to 3.5 billion years ago, when life first appears on this planet. The planet forms, life appears almost simultaneously. Extremely quick from a geological perspective. Well, that is the same period, 4 to 3.5 billion years ago, when Mars had water. And so it's this comparison of early Earth and early Mars, their similarity during the time when life first appears on Earth. So if Earth and Mars are similar, they both have water, they both have volcanism, they both have a carbon dioxide atmosphere, they both have many of the same features, and if during that time life originated on Earth, then the question is, did life originate on Mars? So that is now the driving question in Mars exploration, and that's the question in the context of that question is the background for the recent interest from the meteorites, which also come from this early period. But before we talk about the meteorites, let me answer the question, if Earth and Mars started off so similar, why are they different now? Why did Mars go bad? Why do planets go bad? Is it bad schools or bad neighborhoods or what? What causes them to lose their biosphere, to lose their lives? Well, it turns out the answer is childhood trauma, which is the answer for many things these days, isn't it? Let's imagine the early Earth. Let's imagine the early Earth had a thick CO2 atmosphere. That thick CO2 atmosphere is important in keeping the Earth warm, the greenhouse effect. It's important today. Without the greenhouse effect, the average temperature on the Earth would be minus 15 centigrade instead of plus 15 centigrade. Make a big difference. It's important, even more important, early in Earth's history when the sun was dimmer. So Earth had a thick CO2 atmosphere, and that kept the Earth warm. But CO2, carbon dioxide, is not stable in the presence of water, shown here with this cloud. The CO2 will dissolve in the water to form a weak acid, which will weather or react in the rocks, ultimately forming calcium carbonate, limestone and chalk, which would precipitate out on the bottom of the oceans and lake basins. Now on Earth, organisms have made use of that process, and they direct the formation of the carbonate so that they can form shells and other body parts. But even without any life at all, carbon dioxide in the atmosphere would turn into carbonate piled up on the bottom of ocean floors and basins. And if that went unchecked, all the atmosphere would be gone. It would be piled up. All the carbon dioxide would turn into solid material. Well, on Earth, plate tectonics carries these sediments down, and at temperatures of around 1,000 degrees, the carbonate is turned back into CO2 and comes bubbling up in volcanoes like Mount St. Helens. So coming out of Mount St. Helens is gases, which are the recycling of the atmospheric gases on our planet, and all that kind of arc volcanism. So while Mount St. Helens may have been an inconvenience for the people living downwind of it, in terms of the biosphere as a whole, that kind of recycling is essential. Okay, that's the Earth. This cycle, by the way, called the long-term geochemical cycle of carbon, or the rock cycle, takes about 100 million years. It's a long-term cycle, and it's not to be confused with the short-term cycling of carbon, say, between plants and animals, which takes about 10 years, timescales of 10 years. This long-term cycling has been important for maintaining the stability of Earth's temperature and CO2. Well, on Mars, the same cycle would go. There'd be CO2, it would form rain, acidic rain, which would weather the rocks, which would form calcium carbonate, but there's no plate tectonics. Mars does not have plate tectonics. It is a one-plate planet. There's no way to subduct the material to depth and cause it to come back up. Mars has volcanoes, but it does not have any arc volcanism. The volcanoes on Mars are not like the ones in Mount St. Helens and the Cascade Range. They're more like Hawaii. It's just a hot spot in the mantle. There's no subduction zones, no spreading centers, no evidence of tectonics on Mars. So you might ask, why does Mars lack plate tectonics and the Earth has it? You think the answer goes back to the size of the planets. Imagine the solar system for a minute. First there's Venus, starting with Venus. Venus, a nice Earth-sized planet. Then the next one is Earth, which is also Earth-sized, of course. Okay. The next one is Mars. Well, Mars is 1/10 the mass of the Earth. It's 10 times smaller than the Earth. The next planet out is the asteroid belt. Didn't even form a planet. It's just rubble out there. And then the next one is mighty Jupiter, big, huge Jupiter. We think what happened was when Mars and the next planet, the planet next to it, were forming, the gravitational perturbations by Jupiter prevented those planets from growing to full size. So in some sense, it's Jupiter's fault that Mars is so small. And being small, Mars cooled faster and its crust formed thicker. Small objects have a higher surface area to volume, so they can't maintain the heat that a large object can. So fundamentally, we think Mars started off like the Earth and may have enjoyed 100 million years or so of Earth-like conditions, and then, lacking plate tectonics, its atmosphere eventually got tied up in carbonates, and we think that's where it is today. And in fact, the mission, the U.S. mission, which is on its way to Mars, successfully having left Earth orbit, one of its jobs will be to look for this carbonate, which should be piled up in the surface in oceans and lake beds. Okay, let me now talk a little bit about the meteorite and answer the question, how do meteorites get from Mars to Earth, and how do we know they're really from Mars? Because the meteorites have given us also important information that say, yes, early in its history, Mars was warmer and wetter, because we have 12 meteorites on Earth that we think came from Mars, 12 rocks. 11 of the rocks come from young Mars. They come from geologically recent Mars, and they show the conditions we see today. But one of the rocks comes from early in Mars's history and seems to be consistent with a warmer, wetter, maybe even biological epoch early in Mars. So everything we know about Mars suggests that it started off wet and warm and then degenerated. Well, how do meteorites get to Earth from Mars? We think what happens is something hits into the surface of Mars. Slam, like an asteroid or a comet, slams into Mars and knocks pieces of it flying in all directions. And if a piece is knocked with enough force, enough velocity, it will have escape velocity and will leave Mars' gravity field and go into an orbit around the sun, where it'll go round and round, and maybe from a chance encounter and gravitational perturbations, it might eventually fall into the Earth. And so we have a lot of rocks on Mars that attest to this process. Well, how do we know they're really from Mars? We also have rocks from the Moon. We have rocks from the asteroid belt. How can we identify the ones that are from Mars? Well, the way we do it is one of the rocks, there's this group of 12 rocks. We know they all came from the same place because they have the same oxygen isotopes in their silicates. It's sort of a chemical fingerprint. They all have the same chemical fingerprint. And one of the rocks, the Shergotite rock, has bubbles inside of it, literally bubbles of gas. And in those bubbles, we find the gas that's exactly the same as the Martian atmosphere. Here, plotted on a log-log plot, is the concentration of gases in the meteorite, the Shergotite, versus the concentration of gases in the Mars atmosphere. And this covers a factor of 7 orders of magnitude, 8 orders of magnitude. And the solid line is the identity, and the circles are the data, and the size of the circle is the size of the error bars. And you can see that over 8 or 9 orders of magnitude, ranging from Xeon 132, both argons, and Mars has a unique signature for the argon ratio compared to any other object, nitrogen, CO2, the gas in that bubble, in that meteorite, is exactly the same as the Mars atmosphere. This meteorite, it tells us two things. One, that this meteorite definitely came from Mars. It also tells us that over the lifetime since this meteorite was formed, some 200 million years ago, which is geologically speaking very recent, Mars' atmosphere hasn't changed very much. And the third thing it tells us by inference then is if this meteorite came from Mars, and if all 12 of them have the same chemical fingerprint, then all 12 of them came from Mars. And that's how we deduce that these meteorites, the old one and the young ones, all came from Mars. What I want to do now is make the point that we really don't have proof right now that there was ever life on Mars. And that's, in some sense, our quest. How would we find definite evidence that there was life on Mars? I think the answer is going to be we're going to have to go to Mars. And so here's a map. I want to point out where we'd want to go, and I want to talk now about the kind of work that we might do to prepare to go to Mars. Where would we go? And I want to talk about two sites. First, let me describe this map. This is a geological map of Mars. And roughly speaking, Mars can be divided into a couple broad categories. There's this domain here in the southern hemisphere, this light tan material. And each crater is marked by a large crater is marked by a brown dot. You can see there's a lot of brown dots here. This southern hemisphere is the ancient crater terrain. It's the southern half of Mars's surface. It's heavily cratered. It's very old. It dates back to 3.5 billion years. The northern region is the smooth lowlands. It's very young. Here's Olympus Mons, and here's the Tharsis volcanism. Well, this region here is the region that's of interest from the point of view of early life. If there was life on Mars, this is where it would have left its remains, in this ancient crater terrain. So I want to suggest that two sites that we might imagine sending a mission to on Mars that would dig for evidence of early life. One site in the equatorial region, a lake site, and the other site in the polar region. And the way we develop our arguments for why we should go there is by going to places on Earth that we think are like that. So let me talk a little bit about the coldest, driest place on Earth. Where is the coldest, driest place on Earth? It's the Antarctic. Here's the Antarctic dry valleys, where the average temperature is 20 degrees centigrade below freezing, and the precipitation is less than the Gobi Desert. It's a very cold, dry place. And when one stands out in these valleys and looks out, they appear completely lifeless, completely dead. But in fact, there's two major ecosystems here where life is hidden in niches that I think will tell us how life might have survived on Mars and where to search for evidence of fossils of that life. The first we do is we go up and set up a camp. This is our camp on the valley floors. And in fact, this picture was taken on Halloween, which is why we were flying the Jolly Roger, in fact. We were waiting for trick-or-treaters. But none of them came. So we ate the candy ourselves. But we study the life that appears in these valleys. And the first and a very interesting type of life is found just underneath the surface of certain rocks. And in fact, Chuck Stearns, who works in the Antarctic too, happened to have one of the rocks and has brought an actual sample here. And this is a close-up picture of that rock. The scale is from top to bottom about 1/2 inch. And just underneath the surface of the rocks, living literally inside the rocks, are lichen and algae. You'd never see it, never know it by looking at the rock. It looks just like a normal rock. But inside the rock are the lichen and algae living. And the reason they live inside the rock is because the rock acts like a little greenhouse. It traps heat when the sun is shining, and it traps moisture. When snow falls on it and the sun can heat up the rock and the snow melts, the water will percolate into the pore spaces of the rock, and the rock will hold the moisture for many weeks after the sun has dried out the rest of the place. So it's literally living in a little rock greenhouse. The second example of life we find in the lakes themselves. On the valley floors, you saw that big white patch on that valley floor. It's an ice-covered lake. The ice cover on those lakes is about as thick as this from floor to ceiling here, and it's there all year round. What we do is we go down there and we melt a hole through the ice cover with this Rube Goldberg device. It's a steam jetty in which hot ethylene glycol is pumped through some coils and literally melts a big hole through the ice. And as it melts, a sump pump sprays the water away. Eventually, we can get deep down so that we're literally inside this ice cube, this big giant layer of ice on the lake. When we pop all the way through, the water fills up to almost to the level of the ice. But now we have a hole where we can go down into the lake into the water, because underneath that ice, 15, 20 feet of ice, there can be up to 100 feet of water, a large liquid pool of water. So what we do is we get a volunteer, a non-essential federal employee, of which we have a lot, and lower them down into the hole, and to understand first, how is it that there could be liquid water in this very cold environment? How can there be liquid water when the average temperature is minus 20 centigrade? And what do we find in there in terms of life? We find that there is life in there. This is a picture from the bottom of one of these lakes. There's algae and bacteria living in the lakes. In this very cold, they're being essentially protected by a layer of ice. You wouldn't think of it, but the layer of ice is acting as a blanket, as an insulating blanket, keeping the water liquid and keeping the water warm and allowing life to survive in an environment that otherwise would not be able to support any life at all. The key thing here, the key feature about the valleys that allows these lakes to exist is not so much that the temperature is minus 20. This is the temperature throughout a year, one of the first years we had continuous data. And indeed, the average is minus 20. But that's not important. What's important is that in the summertime, for just a couple days each year, the temperatures get above freezing. And when that happens, the glaciers melt and the meltwater flows into the lake. And it's that source of meltwater that keeps the lake liquid. Because in order for that water to freeze, it has to release the latent heat of fusion of water, some enormous 80 calories per gram, which must diffuse through the ice cover. And it's that is the limiting rate determines the thickness of the ice and the presence of liquid water. Well, we now have an explanation for how life can survive in a lake in the Antarctic long after conditions are much too cold and dry for life. What does this mean for Mars? Let me just show you that we could do the same calculation for Mars and show that after Mars started getting too cold for life, we could have had lakes like the dry valleys for 500 million years. So what we're saying is that on Mars, as it got colder and drier, life could have retreated into these ice-covered lakes, and that the last stand of life on Mars could have been a swim in an ice-covered lake like we see in the Antarctic. What it means, what it's telling us, I think, is that when we go to Mars, we should look for lakes, because a lake would be what the last organism, the last Martian organism might have lived in. In addition to being a good place to live, a lake is also a good place to die. Don't do this at home. I'm not recommending it. But a lake is a good place to die because if you die in a lake, your body settles down to the bottom and can get preserved in the sediments. Now, remember all those river features I showed you? Would those be places to go to Mars to look for fossils? No, because the river would be washing away any sediments. We need to find a place where sediments are accumulating and being preserved. And a lake provides just such an example. So what we want to find is a place on Mars where there was a lake. And this is the best example we have right now of what was probably a lake early in Mars history. This is a canyon, Hebe's Chasm. It's in the Valles Marineris Canyon system, just on the equator of Mars. Here's the scale bar, 0 to 100 kilometers, 60 miles. So this is about 150 kilometers across and about 300 kilometers long. It's a canyon. In the middle of the canyon, there's a plateau. And if you look closely, you can see that there's lines, laminations on the side of the plateau. We think that this plateau was deposited, or sediments that were deposited when this canyon was full of water. So this was at one time a giant lake, and we think it was full of water early in Mars history and remained full of water for billions of years, at least a billion, maybe more. We think these sediments could be carbonates, and they could be holding evidence of any organisms that lived in the lake at that time. So the number one place that I would like to go on Mars is right on this plateau and drill down, dig down, or whatever, down and get sediments from deep down. Well, it's kind of risky because the sides, this plateau stands up about a mile, 2 miles high, and the sides of the canyon's wall here are about 4 miles high. And if you look at this, this is 100 kilometers. The error bar on the Pathfinder mission, for example, is 160. So it would say that you have a good chance of landing anywhere in a circle about this size. Well, that means you have a good chance of hitting the side of a cliff and rolling down a couple miles before you reach a landing. Well, that's not something that project managers like. So they would not land in a place like this. They want us to find a lake bed that's more convenient to land at, maybe one that's near an airport or something. So this is our best site, but we can't go there. So we've been looking for other sites. And here's another one, which is a lot smoother and a lot easier to land at. This is a big flat crater going around like this. It's called Gusev Crater. It's about 100 kilometers in diameter. It's a nice big flat area, and there's a river flowing up. It's hard to see it, but down here there's a river flowing up into the crater that has filled this crater with sediments. So we think at one time this was a crater lake on Mars, and it's been filled with sediments, and here would have been an ice-covered lake as well. And that these sediments, nice, smooth, and flat, could have been deposited in water and might also hold carbonates and evidence for life. So our target mission, in fact, it's a mission that we're pushing that we hope would be a joint mission with the Russians, would be to land a rover in the middle of this crater lake bed, because it's nice, big, and flat, and then we drive the rover. Eventually, I would propose that we drive the rover and head up the creek. We wouldn't have a paddle, but that's all right. And search for, as we cross the shoreline, we would search for evidence of life. We'd search for fossils. We'd search for carbonates. We'd search for proof that this was once, indeed, water-filled crater. And this, I think, is the best possible place on Mars, based on our current knowledge, for searching for fossils. What else might we look for besides fossils? We might actually find organic material. And we also find organic material in the meteorites, which is why we're encouraged to think we might find organic material on Mars. How can we tell organic material is of biological origin? This is what I mentioned earlier. There's a distinct signature, which I want to now explain. This is the same diagram of age from 4 billion years ago to now, and it shows the carbon in the sediments on Earth. And it shows a characteristic shift between the inorganic carbon, the carbonate, and the organic carbon. And this, on the axis here, is what's called the del 13. What it really is just the enhancement of one type of carbon over another. There's two types of carbon. One has one more neutron in the nucleus. Carbon 13 has one more neutron than carbon 12, so it's a little bit heavier. Well, biology is enhanced in the light carbon. We have more light carbon in us than, say, the atmosphere does. And that signature, 2% more carbon-12, has persisted throughout Earth's history, and it's a characteristic signature of life on Earth, and has been throughout Earth's history. We could imagine that if we find organic carbon on Mars, it might have the same shift. And in fact, recently a group in England studying one of the meteorites reported that they had found organic carbon with this same shift of minus 20 parts per mil, or 2% lighter carbon. So this kind of evidence we would try to get at for evidence of that the carbon we were seeing was really biological. But it'd be nice to find fossils, it'd be nice to find organic material, but even better to find an actual Martian organism, an actual Mars bug, right there, still intact, that we could dissect, micro-dissect or whatever. Is there a chance we could do that? I think the answer is yes. And again, it's based on places on Earth as an analog. So let me talk about that now. This is Siberia. This actually is Siberia, California. It's not Siberia, the real Siberia. But the real Siberia, this is the real Siberia. This is a station, a geological station. And Siberia is not like Mars. You might think it's not like Mars at all. In the summer, there's Russians and bears and dogs and grass and billions and billions of mosquitoes. But what's interesting is that underneath the surface, out in the tundra in Siberia, we're at 70 degrees north. This picture's taken at 70 degrees north, up within the Arctic Circle. And here's the tundra. Underneath the tundra is frozen ground, the oldest continuously frozen ground in the northern hemisphere. We set up a little drill. That's what this is. It's operated by 3 people. And we drill down into that frozen ground. It has been frozen at minus 10 for 3.5 million years. Minus 10 centigrade, about the temperature of a good freezer. So imagine taking something like the leftovers and putting them in the freezer and leaving them there for 3 million years. That's what we're seeing when we drill down into this permafrost. We know the age from geomagnetic reversals, and we know that it's been continuously frozen from the morphology of the ice wedges. So continuously frozen for 3.5 million years. And what do we find? we find that there's organisms, viable organisms, in those sediments. So what we find is that in Siberia, at -10, we have organisms, microorganisms, bacteria, that survive for 3 million years. That's 3 with 6 zeros, right? 3 million years. Now on Mars, we want survival for 3 billion years. Well, billions and millions, you know, they sort of rhyme, and if you're fast, you can get away with it, but there's a big difference. There's 3 extra zeros, right? But it's also a lot colder on Mars. It's -70. Okay, well, colder means longer survival, right? Deep freeze, food keeps longer than in a regular freezer, right? Well, there's this thing called the Q10, which is the reduction in activity for every 10 degrees in temperature, and value for 3 is not outrageous. And if every 10 degrees reduces or enhances survival by a factor of 3, then 6 decades in temperature, 3 to the 6 very neatly generates the factor of 1,000 that adds 3 more zeros to our survival number. So you might imagine that we would go to Mars maybe with the same drill and the same Russians, go to the South Polar regions, drill down, pull up some permafrost on Mars that's been frozen at -70 for 3 billion years, warm it up, and find viable organisms. Well, the answer is no, unfortunately. Not because of this analysis. Temperature would be okay. The answer is no is because of radiation. Last year when we were in Siberia, after we pulled out the microorganisms, we lowered a specially built Geiger counter down into the hole and measured the naturally occurring radioactivity in the soil. Just from the natural crustal average abundance of uranium, thorium, and potassium, there would be a lethal dose of radiation for these microorganisms in about 10 million years. What that means is if you go lie in the permafrost for 10 million years, you will be dead, guaranteed. Maybe not in 3 million years, but in 10 million years for sure, just from the radiation. And it's not necessarily enhanced in this place. It's just the average abundance of uranium, thorium, and potassium. These are airborne sediments. This isn't bedrock with high uranium or anything. On Mars, that same crustal average abundance of uranium and thorium and potassium would be there. Organisms would still accumulate a lethal dose in some 10, 20 million years. And over 3 billion, they would have accumulated 300 lethal doses. They would be dead as a doornail. Now that might actually be a good thing. I mean, you're pulling up a Mars organism and warming it up, maybe you're happy that it's dead. But it would still, the important point is it would still be there. Even though it's dead, it would actually be there. The actual biomolecules that make up the organism were there. You'd have the body. Unlike a fossil, usually the body is gone. All that's left is a print. And in the organic material, in the meteorite, for example, it's been completely altered. It has no resemblance to the organics that formed the organism itself. But here, in the South Polar regions, we might be able to exhume a Martian and actually do a post-mortem on it. Look at its amino acids, for example. On Earth, we know that all life is based on the same 20 left-handed amino acids. Well, maybe on Mars, they're all right-handed. Or maybe they're ambidextrous. Or maybe they don't even have amino acids. So we could actually study the detailed biochemistry and make a comparison to Earth. And this is an important point. I want to now turn to this sort of philosophical issue of comparing Mars life to life on Earth and use it as a way of addressing the question of why is it interesting to search for life on Mars? Why do we care? What will we learn? Well, the way to answer that question, I think, scientifically, is to first look at one of the amazing facts we have about life on Earth, which is that there's only one example of life on Earth. It's all the same stuff. We're all the same organism. This is shown in this diagram. It's called the tree of life, which shows the phylogenetic relationship of all life. This green line is what we normally think of as life. Plants are here, animals are here. This is all called the eukaryotes, and that makes one tree. Then there's these other two trees, which are the bacterial tree, the prokaryotic trees. There's the bacteria or the eubacteria. These are the things that the E. coli in our stomach and things that make yogurt taste so good and other things taste so bad are in this tree. And then here are some of the so-called archaea or archaeobacteria, which are some exotic bacteria. What it shows is that all life on Earth fits on this tree, and all life on Earth is hence related. And there's no a priori reason why this had to be the case. We could have imagined that all life on Earth formed 3 distinct branches, or 3 distinct trees, or 2 distinct trees that were not related to each other. completely different. But they're not. There's only one life on this planet. The same 20 basic amino acids, the same genetic sequence. In fact, if you take E. coli out of your stomach, which is one of the eubacteria, and look at its ribosomal RNA, and you compare it to your own ribosomal RNA, we're up here in animals, at least most of us are, there's a similarity at the 50% level. There, we are closely related, all life on Earth. Well, that's interesting, but it makes it hard to compare, and it reminds me of the metaphor of comparing apples and oranges. And people say you can't compare apples and oranges. But in fact, you can compare apples and oranges. In fact, you have to compare apples and oranges. This is a plot of apples and oranges being compared. This was put together by Scott Sanford and was published in the Journal of Irreproducible Results. But it makes an interesting point that suppose you wanted to understand fruit as a broader category, you'd have to compare apples to oranges, and you'd have to compare them to bananas and tomatoes as well, which is also a fruit, even though legally it's defined as a vegetable. Okay. And this is the point as well with life. On life, we've only got one. We've only got apples, or oranges, depending on how you want to do it. We only have one, and if we want to understand life at a broader level, at a more general level, we need to have something to compare to. And that's why scientifically, I think, finding an example of a second genesis, a second instance of life, would provide fundamental biochemical insights. We can hardly imagine what they would be, but certainly to generate all sorts of new biological weapons and medicines or whatever, depending on who's funding the research. So this is, I think, the most compelling scientific answer for why do we care to find evidence, and why would we be driven to find the actual biochemical substance of life itself, not just the fossils, not just the proof that there was life there, but to actually get our hands on the Martian biochemistry. Philosophically, of course, it opens up the question of are we alone? What's our role in the universe? If we find life on another planet that's different from ours, then I think that would be compelling evidence that life is widespread and that every solar system from here to there is just loaded with life whenever there's a planet like Earth. Let me now talk a little bit about future exploration. I've been talking about life. I've been talking about searching for fossils, digging up Martian organisms, comparing their biochemistry to our biochemistry. I argue that this is the kind of science that is uniquely enabled by having humans on the job. Humans know how to do these sorts of things, operate drills and study life. And in fact, you might argue that it's very hard to recognize life. It's very hard to define it. And a lot of times when people say, how will you know it? I say, well, we'll just know it when we see it. It takes life to find life, to recognize it. And so I think that the first scientists to go to Mars are going to be biologists. In fact, here's an artist's conception of a bunch of biologists trying to fix their rocket engine. They're going to be stuck on Mars for a long time. But this is the science. Most space sciences don't need humans. In fact, for most space sciences, humans just get in the way. You don't need them for the telescopes or the seismometers or the meteorological stations. They're just a bother. But when it comes to biology and paleontology, I think that's where humans are going to outperform the machines. Currently today, we only know how to do this kind of research with human beings. When we imagine humans going to Mars, we have to ask the question, what is Mars's future? Now, I want to close with this slide, which I think in some ways sums up the whole talk and leads on. We know, I've been saying that Mars is a planet with a past, and its past has been a past that's been Earth-like because it had water. Water is the essential requirement for life. We think we understand, or we have theories for how it became the cold, dry world we see today. We'd like to go to this world, dig up evidence of this early time, find out if there was life there, and look at it. But the fact that Mars had a past means that it might also have a future, of course. And it raises the question, could we bring it back to life? Could we do CPR on this dead planet? Bring it back to life. Bring back that loving feeling that Mars once had. And I think that that's an interesting question. And the answer is actually pretty straightforward. What would you have to do to bring Mars back to life? Well, what you have to do is warm it up. Well, we know how to warm up planets. We're warming up this one. And in fact, if we were to do exactly what we're doing on Earth, where it's probably not a good idea on Mars, it might warm back up. And as it did so, if any of those organisms were frozen in the permafrost and still alive, they would recolonize Mars, and it would be Mars for the Martians once again. And if not, one could imagine carrying basically Earth's genome to Mars and seeding it directly. Let me stop there, and maybe we have time for some questions, Sanjay.
I think we have plenty of time for some questions for Chris. Could we have the audience slides turned up a little bit? Question.
How many cars would you have to bring to Mars in order to produce?
Really? Well, it's not so much the cars, because cars just produce CO2, and CO2 is not a very efficient greenhouse gas. In fact, what one would want to produce on Mars is these so-called super greenhouse gases, like good candidates are methane, nitrous oxide, CFCs, well, actually mostly fluorinated carbon compounds and things like SF6 and whatnot that can have thousands of times the efficiency of CO2 at creating a greenhouse effect. So you can imagine introducing those in the atmosphere of Mars, and as the planet warmed, any CO2 in the regolith or the polar cap would come out, and you have a positive feedback, which would, on relatively short time scales, hundreds of years or so, could transition Mars back into a warmer, thicker state if there was enough exchangeable CO2, which we don't know.
And how would you produce those gases?
Well, if Mars has the expected cosmic abundance of things like fluorine in its crust, then you could produce them there. You couldn't imagine carrying them from Earth. This idea was originally suggested by James Lovelock in a book called The Greening of Mars, and he proposed carrying them from Earth. But in fact, just simple back-of-the-envelope calculation shows that you need 10 to the 12 shuttle launches or something. It's just out of bounds. But making it on Mars is another thing. And a third possibility is the idea that there are some microorganisms on Earth that are able to couple to these, in particular, say, the halogens. They can decompose the halogens. And maybe anything organisms can eat, they can make. So one might imagine eventually a biological system which couples to that.
This question over there.
What would happen if you created ozone layer like on Earth, but then on Earth you destroyed it again?
Well, on Earth, the ozone layer is created by the presence of oxygen. For most of Earth's history, Earth did not have an ozone layer. And early in its history, then when the plants made enough oxygen that there's oxygen in the atmosphere, the ozone layer was created naturally. And in fact, humans will not be able to destroy the ozone layer in any real sense. We'll be able to thin it enough that it's a problem for us. We are very sensitive to ultraviolet light. But a lot of organisms on Earth couldn't care less, even though we personally will. As long as there's oxygen in our atmosphere, we'll have a substantial ozone layer. Not substantial enough. So on Mars, if you wanted an ozone layer, you'd have to first make an oxygen atmosphere. And that's very difficult. When I showed Mars having a future with water, all it had was a thick carbon dioxide atmosphere. All we've done is bring it back to the way it was early in its history, the same way the Earth was early in its history. If you wanted to bring an oxygen atmosphere, then you'd have to make sure that there was enough plants on Mars and give them enough time that they could build up an oxygen. And that would take a long time. At the present efficiency of the Earth's biosphere, it would take 100,000 years to make an oxygen atmosphere on Mars. So don't hold your breath, so to speak. Oops, okay, you're going to call the question?
Go ahead.
The question was, has water left Mars for good? The answer really is we don't know. We know that Mars started off with at least this 500 meters of water, and we know that water is leaving the top of the planet now. But if you just take the rate at which it's leaving now and just sum that over the history of the planet, it only turns out to be about 2 to 3 meters. Now, it could be that the rate was much higher, the loss rate was much higher, and in fact, in the Mars atmosphere, we see enrichment of the heavy isotope of hydrogen, deuterium. And that may be telling us that the escape rate was higher, but it's very hard to know for sure, and there's other ways to explain that. So the real answer is we don't know. In addition, in the polar regions, we see evidence for ground ice in the morphology of the craters. So Mars had a lot of water. It might have escaped to space, or it might be trapped in ground ice in permafrost, and then it would be liberated if the planet was warmed. But we don't know the answer to that definitively. Right. No, that's a good question. Mars is smaller than the Earth, 10 times smaller, and its gravity is 1/3 the Earth's about. And so it can lose its atmosphere to space more easily. But that's not the limiting factor. And in fact, a good way to understand that is to think of Titan. Titan is even smaller than Mars, and it has an atmosphere thicker than the Earth's. Titan is the largest moon of the planet Saturn. So a small object can hold a big atmosphere. And I think the main loss of Mars's bulk atmosphere, the CO2, we think was the carbonate formation rather than, in fact, escape to space.
There was one question by kid in the third row. Did you have a question?
So what exactly would you have to do to warm up Mars?
Well, I think there's many ways to warm it up, but probably the most effective way, and the way that we already know how to do. In some sense, it reminds me, this argument reminds me of a Dennis the Menace cartoon where Dennis and Margaret are arguing. And Dennis says, "I'll bet you $1 million that I'm right." And Margaret says, "I'll bet you a nickel that I'm right." And then Dennis goes, "A nickel? Well, now you're talking real money." And the point is that if we talk about warming up Mars using warp drive and antimatter engines, well, that's like betting $1 million. It's not very interesting. But if we can say that it's possible to warm up Mars doing the same thing that we're already doing on Earth, then that's a near term and a possible and much more interesting. So when I was looking at this problem, I only looked at things that we already know how to do. So clearly, if we invent warp drive, then warming up Mars is easy. But given what we already know how to do, how would we do it? And the answer is the only thing we really know how to do is put into the atmosphere super greenhouse molecules. And we're making them at such a rate on Earth that if we were to make them on Mars at exactly that same rate, Mars would warm up in 100 years or so. So in fact, not that that's necessarily the way that will actually be done if it's ever done, but this just shows that there's a possibility that we could do it with present technology. And the question is no longer a question of can we, it's now a question of should we and will we, which are very different questions than the scientific question of can we.
Question.
My question goes to this issue of the concept of warming up Mars. From what you have presented, it sounds like the original problem of Mars wasn't its cooling from the outside, but its internal cooling.
Internal heating, yeah.
And by adding greenhouse gas, you're not going to add internal.
Right.
And you don't
Right.
easily turn limestone back
Nope.
into carbon
Nope.
dioxide. And so, I mean, it doesn't, I mean, those
You haven't fixed the fundamental problem. That's right. If we were to warm Mars up, we would not have fixed the fundamental problem, which is that Mars is too small. Now, by the way, I just add in the footnote here that we think that if Earth was where Mars is, it would still be habitable. It's not the intrinsic distance from the sun that makes Mars inhabitable. It's its size. If Mars had been Earth size, or more specifically, if Earth was where Mars is, it would still be habitable. It'd have a slightly higher CO2, but we would have evolved to adapt to that, and we'd like it, in fact. Our blood would be more carbonated, sort of like Pepsi or Coke, you know. We'd enjoy it. But your point is well taken that if we were to warm Mars up, we haven't fixed the fundamental problem that the planet lacks plate tectonics, and one does not start plate tectonics on the planet in terms of our technology. And so certainly on timescales of 100 million years or so, it would wind back down. But the way I think of it, you're spreading the mortgage payments out over 100 million years. Now that's short compared to the geological ages, compared to the age of the solar system, but it's long compared to human time scales. So it's not a permanent fix. Nothing is permanent, really, in that sense. When we look at it, eventually there'll be problems even with Earth as the sun goes red giant or some other calamity hits us. So it's just a question of how long will it be habitable. And the answer for Mars is about 10 to the 8 years. And then somebody else has to come up with a better idea.
Question.
I understand that, I'm going to bring us back to the present. I understand that for the next 10 years, every 2 years, NASA's going to be sending spacecraft to Mars.
Right.
And I understand that the Pathfinder mission is one of the more engineering robotic missions.
Right.
Where is this all leading to? In other words, the 10 years, we have small delivery systems where the Russians have Proton, which ended up, as you said, in the Pacific.
Right.
Are we going to start developing those? Is NASA going to start developing those larger systems that are going to mean larger spacecraft getting out there after the 10 years? Where are we going? And how is Phobos going to be?
Let me answer the last one first. Currently, there's not much interest in going to Phobos or Deimos, the moons of Mars. The Russians had a mission, and it failed about two years ago. And so there's been I haven't heard any revived interest. on Phobos. The focus of interest right now is really on the surface of Mars and the subsurface and searching for life and searching for water, searching for evidence of early water. There were supposed to be 3 spacecraft launching from Mars right now. One's on its way, the Mars Global Surveyor, and Pathfinder, as you said, will launch in a month. The Russians launched one last Saturday, which landed in the Pacific Ocean Sunday. So it was very unfortunate. I was particularly unfortunate. I was the principal scientist for the U.S. instrument. This was a Cold War remnant, and the U.S. had a token instrument on it, the MOX instrument. And I've been the principal scientist on working on it for 5 years, and splash, there it goes. You know, it makes the data analysis problem easy, at least, I guess. And the U.S. has a program of every 2 years launching 2 missions to Mars. There are small missions, but I think that it's going to be very interesting because Mars is a really fascinating place, and I think as we get more data about it, we'll learn things that we're just guessing at now, and that will tell us which way to go. And I think the way I predict it is that if these missions start returning interesting data, like definite evidence that there was a lake bed and some suggestions of sites consistent with life, then the program will accelerate. It will go to bigger launches and whatnot. The other thing is, a reporter called me up, you know, to sort of interview the relatives of the victims, sort of thing, right? About Mars 96. You know, what do you think of your baby landing in the Pacific Ocean? You know, that sort of thing. And I said, well, you know, it's an optimistic way of looking at it. When the United States lost the Mars Observer, it was a turning point in our Mars program. The headquarters sat down basically with a clean sheet of paper and said, let's design a Mars program from scratch and let's do it right. And the Mars Surveyor, the Mars program, the Surveyor program came out of that, which is a nice program, launches constantly and avoids the sort of sporadic wait 20 years and then launch everything but the kitchen sink approach. And that's nice. And I think, well, maybe what will happen as a result of this failure of this technically joint mission, the U.S. and Russia will sit down and say, okay, let's start with a clean sheet of paper and let's figure out what we're going to do jointly on Mars. And maybe the answer will be we'll send a rover to Gusev Lake and search for fossils. And that's a good melding of capabilities because the Russians have the big launcher, the very reliable Proton, except for this one instance. It's a very reliable launch system. They have the locomotion capabilities in terms of big rovers the size of this desk. We have the electronics and sensors that can sit on that rover and the deep space network to talk. So the combination is great. And maybe this disaster will sort of pave the way for a more meaningful cooperation. I mean, that's my Pollyannish view on it, but we'll see what happens.
There's one question way back there.
Venus's atmosphere is predominantly carbon dioxide with a few percent nitrogen. Right, it's 90 bars CO2 and a few atmospheres of nitrogen. Earth also has 90 bars of CO2 and 2 bars of nitrogen. It's just on Earth, because of this cycle of the feedback, most of that CO2 is tied up as carbonate. And about half of the nitrogen is tied up as organic. So Earth's atmosphere that we have is sort of the default, the leftover. The nitrogen that stays up there by the action of denitrifying bacteria and whatnot. So what does that all mean for Mars? It means that probably Mars had a substantially larger carbon dioxide and nitrogen atmosphere as well. And the ratio of nitrogen to CO2 was probably like the Venus and Earth thing, 20 times as much CO2 as nitrogen, roughly 20 to 1. Interestingly, the present ratio of CO2 to nitrogen in the present Mars atmosphere is 20 to 1. So that's a puzzle. How did they maintain that ratio? But presumably it must have had a much thicker, if you just do a simple scaling from Earth, mass scaling, you would expect 20 bars of CO2. If you make something a little more subtle than just a simple mass scaling, you come up with more like 5 or 10 bars. So we think that there's a lot of CO2 buried as carbonates. We just don't know. And that's hopefully something Mars MGS will tell us, Mars Global Surveyor, because it will have a thermal emission spectrometer that will be able to detect carbonates if they're exposed.
Frank Sherb.
Well, what we think is happening is that you have all these volatiles in the solar nebula, and the carbon will either be in the form of methane or carbon dioxide, and nitrogen will either be in the form of nitrogen or ammonia. And if the early solar system did not have a lot of hydrogen, if it wasn't reducing, then the carbon and nitrogen go into their oxidized states. And so CO2 and nitrogen would have been the volatiles that accreted on the early Earth. Even if they accreted in the reduced form as methane and ammonia, rapidly there would have been loss of hydrogen due to photodissociation of methane and ammonia, because they both are unstable with respect to UV light, and the loss of hydrogen. You end up with an oxidizing environment in all cases. Early on, in the 50s, we thought that Earth formed in a reducing atmosphere, and that life formed while it was reducing, and then it transitioned to an oxidizing one by the loss of hydrogen. Now we think that Earth formed with a CO2 nitrogen atmosphere based on the oxidation state of, say, comets would have been a likely source of volatiles. If you take a comet composition and let it come to thermal equilibrium at 300 degrees Kelvin, the dominant form of carbon is CO2. It's non-negligible amount of methane, but the dominant form of carbon is CO2. Nitrogen is exclusively in the form of N2. Sulfur is SO2, and so on. It's all in it's on the border, but it's more oxidizing than reducing. So now we think that, in fact, the planets accreted their volatiles in their oxidized form. And the amount of carbon on the Earth is not surprisingly large. Earth is not a carbon-rich planet. In fact, the C to Z, where Z is all elements heavier than helium, the C to Z ratio on Earth is 10 to the minus 4 solar. So we are a carbon-depleted planet. It's just that the small amount of carbon there is very near and dear to us, and we make good use of it.